Let's look at an example of how we can find the Thevenin and Norton equivalent circuit. Here I have the circuit same as the one I used for the superposition. Okay, here I'm illustrating the process. We have a little more complicated circuits. The example in the Python code, if you go to, so this is the example I use for superposition in the Python code. It's a little bit more complicated than we have. In this case, we have 3 sources. In this case, you need to have different ones. You need to have the 3 different types, 3 different partial solutions, right? You energize one source at a time, so you solve this circuit 3 times and add the solutions. Check that out. For the Thevenin equivalent circuit, we have this resistor, and we're trying to find the Thevenin equivalent circuit seen by these 2 ohm resistor. And basically, I want to find the Thevenin equivalent circuit in this dotted box here, right? To find Thevenin and Norton, I need to find Z sub t and Z sub n and V sub t and V sub n. Right? These are the things we're trying to find. For Norton, we find the current source, the Norton equivalent the current. And in this case, we do the 2 different ways. We do the open circuit and we do the short circuit, and then we can find. So the first one, we do the open circuit, V sub OC. And in this case, if I do the open circuit, and this current is 0, so therefore the voltage here is 0, right? The voltage here is 0. And so therefore, the voltage here would be equal the current. This current would be equal, let's see, I, X, and let me use a different rule. Let's use IC, and this is V sub C. And in this case, my VOC should be equal to this voltage here. Now here we're using another KVL. Okay, so you really need to have this concept really fully understood, and you can apply anytime you want. So in this case, I'm doing what? I'm doing this one here. So sorry for the noise. So there's some construction going on in our neighborhood. And in this case, we have V sub OC would be equal, this voltage drop, that should be equal to voltage rises, right? Let's see. This is voltage drop. Yes, we need to add other voltage rises. So in this case, from negative to positive, that's the voltage rise. And from negative to positive for the source here, that's another voltage rise plus 12. Right, so what is VC? V sub C is equal to, that should be equal I sub C times that impedance, which is negative J5, and plus 12. And then what is I sub C? Well, I sub C is, since here, if you apply the KCL at this point, so I sub C is the leaving currents, right? That should be equal entering currents with this current source here, J2. And there's another, this one is 0, so that's it. So I sub C should be equal negative J2. It should be plus J2, not negative. So that should just be J2 times minus J5 plus 12, which is, so negative J times J, that's the 1. And so that's a 10, so that's a 12 volts. Right? And the for the short circuit current, so the short circuit current here is, let's see, I shorted that pair of nodes, and now I try to find an ISC. So in this case, let's see if we have any quick way of finding these. So in this case, you could use superposition, right? So, or you could use source transformation, right? So if you use a source transformation, I can transform this, first transform this one into the parallel source, and right? And then do the source. So let's do this. So let's do ISC is going to be equal. So in this case, I transform this to the source transformation, and what I end up with the circuit is this. Negative J5, right? So negative J5, and I have 12 divided by negative J5, and I have J2. That's it. So this is J3, and this is ISC. What I can do is these two in parallel, right? So I can add them together. Now I can use the current division, and so ISC would be the impedance. This we use the other impedance. Remember, we use the other impedance divided by the sum of the impedance, which is sum of the impedances negative J5 plus J3. And in this case, multiply the total current, which is 12 over negative J5 plus J5. Right. So let's see what this short circuit current is. This short circuit current is actually I had a mistake here. Is this should not be this should be not J5. This is the current J2, right? So this should be J2 as well. Let me just erase this. So this should be J2. And in this case, I have J5, so I have minus J2. What I get here is 2.5, right? Times what's inside this is 2.4J plus 2J, which is 4.4J. 4.4 times 2.5, that's 11J. This is the short circuit current. And now we have ZT. It should be equal Z sub n. And that's equal to the VOC over ISC. VOC is 22. And ISC is 11J, so I get that's equal negative J2, negative 2J ohms, and of course VT is equal VOC, that's equal 22 volts, and I sub n is equal I sub SC, that's equal 11J amps. So this is the all the parameters we find for the Thevenin and Norton equivalent circuit seen by that 2 ohm resistor, right? As we said before, you can find this impedance by looking back if there's no short circuit, if there's no dependent sources, and by turning off all the sources. And in that case, by using the looking back method, we can also find the Zn, Z sub n. In this case, let me redraw the circuit. And in this case, I have the, let me just move up a little bit. I have the impedance here. Used to have voltage source, so that voltage source is going to be short circuited. And I have the inductance impedance here. Then I have a both current source here that become open circuit, and this is pair nodes where I want that's seen by this 2 ohm resistor. So I can get Z sub T. By the way, this is J3, this is minus J5, and we find Zn. Either way, the Z sub T should be equal to Z sub n. This looking back the equivalent impedance, just a series connection. These two impedances, which is J3 minus J5, that's equal to J as we find, negative 2J as we found in the using the open circuit and open circuit voltage and short circuit current. Okay, that's the example. The procedure we use is always find the open circuit. That's a safe method. Open circuit voltage, short circuit current. Those correspond to the Thevenin voltage and the Norton current. and then we'll find the impedance by dividing that open circuit voltage by that short circuit current. The shortcut is, if you don't have any dependent sources in the circuit, you can find the Thevenin and Norton equivalent circuit for it, that you can just turn off all the sources. Turn off means the current source is replaced by the open circuit, the voltage source replaced by the short circuit, and then find the equivalent impedance using the series and parallel connections. Okay, that's it for this example.